Okay, so to introduce Chapter 5, in Chapter 5 we're going to be talking about a bunch of different segments and angles within a triangle. So we're still going to stick with triangles, but we're actually going to get away from the proof stuff, and we're going to talk about how different points and lines and line segments within a triangle relate to each other, because we actually have quite a few interesting properties. 5.1 is a pretty, don't want to use the word easy, but a pretty easy topic. It's just going to be one topic. But throughout the whole chapter, there's going to be a lot of vocab and pictures that you might want to draw. So I highly recommend taking good notes for Chapter 5, just because there's so many things that look the same but kind of get confused with each other. So that's my little warning. Today's not going to be so bad, though. So all we're going to talk about today is what's called the mid-segment of a triangle. So the mid-segment of a triangle is a segment that connects two midpoints of two sides of a triangle. So for example, if you have this triangle down here, all of these blue lines would be considered mid-segments, and that's assuming that this point is the midpoint of that side, this point is the midpoint of that side, and then finally this third point is the midpoint of this side. So these blue lines segments are mid-segments of triangles. And the mid-segment theorem says that a segment connecting the two midpoints of a triangle is parallel to the third side and is also half as long. So what that means is this blue line here that I'm kind of going over is parallel to this line, meaning that they have the same slope. They're never going to touch in that whole thing. And it's also half as long. So it's half the length from here to here. So in theory, it's actually just the length of one of these little chunks. So this length here is the same length as that. This length here is the same as this. And this length here is the same of each of those. That's really the only rule today. It's going to be a pretty quick lesson. So here, just kind of using that idea, being told that UW and VW are mid-segments of triangle RST, can you find UW and RT? So we're asked to find UW, that's a mid-segment here. We know it's half the length of the side it's not touching, so if this whole thing is 12, UW just has to be 6. Kind of going the other way, if we want to find the length of RT, we know it's not touching 8. 8 is half the length of RT, so RT has to, as a whole, be 16. So the main thing here is, are you doubling or are you cutting in half? And in general, longer side you're doubling, shorter side you're cutting in half. Let's try this one. This one uses a little bit of algebra. So we're told YZ is a mid-segment of the triangle, and YZ is equal to 3x plus 1. That's this length here. And then we're told MN, this entire length here, is equal to 10x minus 6. And our goal is to find the length of YZ. So that means we need to solve for x and then plug it in to solve. Now, don't be lazy and don't just say, oh, 3x plus 1 equals 10x minus 6. Obviously, 3x plus 1, that length is not the same length as MN. MN is longer. In fact, from our mid-segment theorem, we know it is double. So we know that MN is equal to 2 YZs, if you want to think of it like that. You could also think that YZ is equal to MN times a half. Either way works fine, but if we were using this idea, I like writing this out first because it makes plugging in my algebra make a little more sense. MN is 10x minus 6. That's equal to 2 YZs, and YZ is 3x plus 1. And now we just play some algebra and solve. We'll use our distributive property, 6x plus 2. Feels weird to work with numbers. We haven't done numbers in a few weeks. Subtract 6x, we get 4x minus 6 is 2. Add 6, 4x is 8. And when we divide by 4, x is equal to 2. But we don't stop there. We want to find the length of YZ. YZ is 3x, but x is 2 plus 1. 6 plus 1 is 7. Quick little follow-up. Obviously, MN would have to be 14. And if we plug 2 in, we'd get 20 minus 6, which is 14. So feel free to pause the video and try this one on your own. If xz is 5x minus 3 and on is 2x plus 34, what's the length of Okay, xz is 5x minus 3. On, this whole thing is 2x plus 34. From the previous example, 2xz's is equal to on. So 2 times 5x minus 3 is equal to 2x plus 34. So 10x minus 6 is 2x plus 34. Subtract 2x. 8x minus 6 is 34. Add 6. 8x is 40, so x has to be 5. And now it's a little interesting. We're asked to find the length of OY. OY is this length here. So we know OY is half of ON, so that might be how some of you did it. So if ON is 2 times 5 plus 34, ON is 10 plus 34, 44. So that means OY would have to be 22. Alternatively, you could have also plugged this into XY because, or XZ, excuse me, because XZ is the same length as OY as we talked about on that first page. Last thing for today, we want to show the midsegment MN is parallel to JK and is half as long. So this is just using our midsegment theorem in the coordinate plane. We're going to use our distance formula and what we know about slope. So we got to do two parts. Let's prove parallel. To show that it's parallel, the slope of JK, remember slope we label with an M, and I'm just labeling this as JK, rise over run, so from J to K we go up 2 and over 1, 2, 3, 4, 5, 6. That obviously simplifies to 1/3. The slope of MN, rise and run, we're going up 1 over 3. Obviously those two things are equal, so we're good. If we want to show that JK is twice as long as MN, or I guess, MN is half as long is the other way to say that. Just use our distance formula. So the distance from J to K is big square root of, K would be, let's label these as points, 1, 2, 3, 4, 4, 5. And J is negative 2, 3. So 4 minus negative 2 squared plus 5 minus 3 squared. That gets us 6 squared is 36. 2 squared is 4. Square root of 40. And then if we want to find the length of MN, kind of running out of room, so I'm just going to fall in down here. We would label this as 0.52, and this is 0.21. So 2 minus 1, or let's start with our x's, 5 minus 2 squared plus 2 minus 1 squared. 5 minus 2 squared is 3 squared, which is 9. 2 minus 1 squared is 1, which is 1. And we get the square root of 10. Now on the surface, it doesn't look like 40 is twice as, square root of 40 is twice as long as the square root of 10. But knowing what we know about square roots, when you multiply by 4 with inside of a square root, you're actually multiplying by 2 because the square root of 4 is 2. If that was a little confusing, what you can do is you can punch both these numbers into a calculator. I can do that now. Square root of 10 is a little more than 3, 3.16. That's an estimation. And if we wanted to take the square root of 40, you get 6.32, which of course is double. So we did show that JK is twice as long and that both those lines are parallel. And that's really it. All 5.1 is playing with this theorem.